Okay, the third of Newton's laws of motion. When two objects interact, the force of the first on the second is equal in magnitude and opposite direction to the force of the second on the first. So, in other words, if we have object 1 and we have object 2, at this point they're separated, right? They're not exerting forces on one another, but when they come into contact, right? Say they're moving with some velocity this way, and this one moving with some velocity that way, and so they're going to collide. And when they come together, then the force of the first object on the second object is equal in magnitude and opposite in direction to the force of the second object on the first. Okay? I think that's pretty easy to understand in terms of just the words, but it comes with some conclusions that are counterintuitive to, well, pretty much everyone. And the example that I'm going to use here to drive that home is to look at a collision between like a Honda and a semi-truck. Now, this isn't obviously the only example that you could go for. There's my rendition of a Honda. And there's a semi-truck. Put some wheels on here. Okay. And say they are again on a collision course. So this one has some velocity that way, and this one has some velocity that way. And so eventually in the middle they will meet, right? And then what the third law tells us is that they will exert forces on each other that are equal and opposite in direction to one another. All right? So the semi will get a force on it that is some number of newtons, and the Honda will receive that same force but opposite in direction. So negative F in the notation that I'm using there. And this is a very counterintuitive thing because we know from, well, hopefully not experience, but we know that the person in the Civic, right, in this little car right there, okay, is going to have a real bad day. And the semi-truck is not going to have a good day, but they are in considerably less danger than the car that they have collided with. All right, and this is all down to their masses, right? If we're talking about a fully loaded semi, we might be talking about something in the range of 15,000 kilograms. And if we're talking about a Civic and say we've piled a whole bunch of stuff into it, then maybe we're talking about 1,500 kilograms for the mass of that object. Okay. So if the amount of destruction visited upon the Civic is far greater than what happens to the semi, then, I mean, how can the third law be the case? And this is something that always throws people, okay? But don't let it throw you, please. The favorite thing for physicists, physics teachers in general, to do with the third law is give you a situation where your intuition is telling you, oh my gosh, that Civic is just going to be destroyed and the semi-truck is going to be unhappy, but is going to be okay. The Civic experiences more force, okay? No, stop it. Tell your brain, okay? I get it. You want to snap off that conclusion and write down some answer that is consistent with it, but it is not the case. Every single bit of experimentation that humankind has ever done regarding the third law has shown that these forces must be equal. So what's going on? Well, look at Newton's second law for a moment. Pardon me. I'm just picking up my palm, hitting the page a little bit. So if we look at the second law and we apply it to the first object, so the Civic in this case, sum of all the forces on the Civic is equal to the mass of the Civic times the acceleration of the Civic. And let's say that all the other forces on the Civic in the horizontal direction, friction and drag and things like that might exist, are pretty much dwarfed by this huge force here from the collision. And so we're saying that negative F is equal to M1 A1. Okay. And I should be putting in these all. There we go. Okay. And so the acceleration of the Civic is going to be negative F divided by M1. And we know, of course, that the net force and the acceleration are in the same direction, so we're expecting a negative number here. And if we were to actually give it a number, say, let's just for mathematical convenience, say that, oh my, really picking up that palm. So 150,000 newtons of force, and we're dividing that by 1,500 kilograms. Okay, so we cancel a couple of zeros here, and we get ourselves that the acceleration in terms of its magnitude and direction is negative 100 meters per second squared. Okay, that's a huge acceleration. If you've ever watched Mythbusters, okay, if you haven't, then you have some YouTubing or whatevering to do, okay, they put all these accelerometers on their test dummies and things like that. And usually if the accelerometer indicates that something has experienced, maybe more than 10 Gs of acceleration, which is about 100 meters per second squared, then that thing is in for a real bad day, okay? So perhaps my force here actually isn't true to real life, okay? But this is going to drive home the point. So if we have on the other side, so we may as well change colors. For the truck, we have the sum of all the forces on the second object, so the truck is equal to M2A2. And if we put in the same kind of stuff, we've got M2A2, and A2 then is positive 150,000 newtons over 15,000 kilograms. And so the semi itself experiences a mere approximately a G of acceleration. I mean, that's clearly noticeable, but is not deadly in any way, okay? And that acceleration is the thing that's actually going to be determinative in terms of, if they're going at some velocity and they cut that down to zero as a result of this collision, and they do it with this massive acceleration so that the change in velocity is very abrupt, we will learn that that results in a lot of damage to the things in the car as well as the car itself. Whereas the experience of the semi-truck and the things in the semi-truck is considerably milder, 10 times milder, in fact, if you just look at the magnitudes of those accelerations, okay? So the abruptness, the violence of these collisions and interactions that you have between objects that are two very different masses is consistent with our day-to-day lives. It's just that we're used to thinking about that in terms of the force, the push, the pull on that object, when in fact, because of the third law, those forces between the Honda and the semi, or whatever it happens to be, interacting, those forces are equal. And so the difference in accelerations comes from, one, the mass differential, and potentially from the combination of other forces that are combining to give you that acceleration, right? We made one big assumption here, which is that this collision force was entirely determinative in terms of the acceleration of the Civic and also in terms of the truck, okay? So don't let the third law fool you. It's easy to state, but hard to interpret, and it's counterintuitive like the other laws tend not to be. So keep that in mind, okay? Another couple of quick hits before we go. Just keep in mind that the velocity here, okay, is immaterial in terms of the third law. You can have a Civic going 1 meter per second, you can have a semi going 50 meters per second, and they're still going to be exerting the same forces on one another. Now, how that velocity changes, well, that depends on how big that force is, how much mass they have, what the acceleration of each object turns out to be, and all of those kind of things. So just keep in mind that the third law is essentially inviolable. And in this case, we've simplified it to be sort of the only force that we're really caring about. And the situations will get more and more complicated as we progress through our understanding of forces. But this is the bedrock. So I hope that this brief introduction to it has done you good, and we'll start looking at more complicated situations in the near future. Thanks for listening.